Alright, so we just finished a quick talk about covalent compounds. Now those were simple covalent compounds. By that I mean their molecules are tiny. They have like really small number of like enough that you can draw it, right? They're not like ionic compounds where it's a never-ending lattice, right? So they're just simple covalent compounds. Look at this. This is just water. That's carbon dioxide on top, hydrogen, chlorine, and it can keep on going. Now, the properties about simple covalent structures is that they'll have really low melting and boiling points, very close to room temperature or below room temperature. Why? Is because those forces that are responsible for their state are really weak. What do we call them? Weak van der Waals forces. It's in the name, guys. It's weak, right? Now, look at this graph below. These are relatively low melting points. What's wrong with my pen? They're low melting points, right? And for the other two, look at that. They're relatively higher melting points. They're higher. So it's safe to say something's happening in silicon dioxide and carbon, which makes it different from these molecules. So for one thing, these molecules are called simple covalent structures. Simple covalent structures, whereas the one at the bottom is a giant structure. These two are giant covalent structures or macromolecules. Now, why do they have these high melting points and even boiling points? Well, we'll have to look at their structure. How are they different from the structure of these guys? We saw how water was arranged, and that's how everything else is arranged as well, right? They have those, the atom is held together, the atoms are held together by strong covalent bonds, but all those molecules, which is the group of atoms, like over here, they're all held together by weak van der Waals forces. That's why it's very easy to melt them. Now, if you change the state of water, it's still H2O. It's just that attraction between the particles that has gone if it changes state from, let's say, solid to a liquid or liquid to a gas, right? Let's continue and let's take a closer look at carbon and silicon, why their melting points are so high. Just to reiterate before we move on, melting points of silica and diamond show that they are not molecular solids with weak lattices. In fact, they exist as giant covalent structures, or you call them macromolecules. Now, diamond, some of you know, is just carbon. Carbon atoms. C for carbon, right? It's just carbon. Now, carbon can make up to 4 bonds, and that's what it does. It makes 4 covalent bonds to each other. So this carbon makes 4 different bonds with carbons all around, and each of these carbons will make 4 different bonds. It's not shown here, but it is shown over here. Each carbon is making 4 other bonds. Not these guys, because you don't want to make this diagram too dirty, but this is again a never-ending lattice. Each and every carbon atom is held to each other carbon atom by strong covalent bonds, right? These are strong covalent bonds. As you saw for sodium chloride, they were held together by strong ionic bonds. So ionic bonds and covalent bonds are really strong bonds. And that makes sense because it's not easy to turn water into some hydrogen gas or oxygen, right? But you can change the state of it because the covalent bonds are not responsible for the state in that case for water. Over here, they are, much like ionic bonds में जिस तरह होता है. So these are really strong. And if a lattice is made of these, solely of these in its entirety, it's very difficult to melt them. We saw it in ionic bonds for every ionic compound there is. Now we're looking at certain molecules that arrange themselves. Now there's no surprise that when you have diamond with you and you know it's the hardest substance on the planet, it also has a very high melting point. I think we saw it's close to 33 or 3500 degrees Celsius. And that's all possible because each and every carbon is bonded to each other with strong covalent bonds. So it's very difficult to melt it, right? Now, if you ever pick up a piece of diamond, now, because each and every carbon is bonded to each other carbon and there's no intermolecular forces, they're all a never-ending lattice of covalent compounds, kind of like drawn here. It's kind of like thinking like when you pick up a piece of diamond, you're kind of picking up a molecule of diamond, right? Because it's all automatically like all connected to each other, covalently bonded. So to think of them as molecule for a diamond is kind of pointless because the entire thing is one molecule. They don't show any special properties aside from insanely high resistance to heat, where they do not melt, and I guess they look pretty. But other than that, they're kind of boring chemically. The same structure what we're looking at diamond gives it special properties. It is a very hard substance because each atom is held in place by 4 strong covalent bonds. In fact, it is it is the hardest substance on the planet. For the same reason, its melting point is really high as well. 3,550 degrees Celsius. There should be a degree over here. Degrees Celsius. It cannot conduct electricity because it does not have any ions in it or any free moving electrons. Another very similar structure to diamond is silica or sand, also known as silicon dioxide, right? Now, silicon dioxide is written SiO2. And how they're arranged is each silicon atom is bonded to 4 oxygens and each oxygen atom is bonded to 2 silicon atoms. Now, it's kind of weird why we call it SiO2. Well, it's because of ratios. For every 1 silicon atom present, you will have twice the number of oxygen atoms in a particular grain of silicon. So that'll always be true, right? And this might not be a good representation because it's a very small sample and it's probably not cut evenly. It's not even cut, it's just a picture that's been cropped, right? So you can probably tell there are twice as many, more or less, oxygen atoms for every silicon atom, right? Because another way to see it is not that there should be more silicon atoms in a lattice because it makes more bonds, but more oxygens cater to 4 silicons and less silicons cater to the 2 bonds of oxygen. Anyway, right? So the ratio between silicon and oxygen is 1:2. That's why this lattice or silicon dioxide is represented as SiO2. Very similar to NaCl, because the ratio between chlorine and sodium is 1:1. You just write NaCl. This is drastically different from carbon dioxide. When we say carbon dioxide, we say a carbon is bonded to 2 oxygens, right? That is the difference. So very easily people get confused. Oh, carbon dioxide and silicon dioxide. Well, CO2, SiO2. Well, they should be very similar in properties as well. No, they do not. This does not bond to just 2 atoms and, just stays like that. Each oxygen also bonds to another silicon, and they all act as a gigantic Lego piece, interconnected, and also that gives it really strong properties as well, like really high melting point, very brittle, just very hard, right? Enter graphite. Carbon has allotropes. An allotrope means that there are 2 different physical forms of the same element. So carbon can either exist as what we just saw as diamonds, Another allotrope for carbon is graphite, or like how you see it as coal and whatnot, right? So graphite. Now graphite is also a very unique, has a very unique structure. Let's see what that looks like. We saw for diamonds that each carbon can make 4 bonds, and that's what it does, right? But over here at graphite, each carbon doesn't make 4 bonds. Each carbon ends up making 3 bonds to other carbons. What happens to the last bond? Well, nothing. And each electron is unbonded for each of these carbons. Each of these carbons has 1 electron free. And 1 electron free, it's free to move around. So what does that mean? An electron is free to move around? Well, it means that that substance can conduct electricity. So graphite is one non-metal that can conduct electricity very easily, right? Now, I think you've seen those experiments in your science class or science books where you shave a pencil in half, shave it off, or cut it in half lengthwise, and the lead in the pencil is exposed. And when I say lead, it's just the material in the pencil. The nib area, that what you use to write, is called lead. It has nothing to do with the metal lead that's on the periodic table. Absolutely nothing to do with it, right? So that lead can conduct electricity, even though it's a very impure form of graphite. It can easily conduct electricity if you connect a battery to it with a light bulb. It'll start conducting. Another special property of or structure of graphite, how it's interesting from diamond, is that these carbons arrange themselves in a sheet, a never-ending sheet of hexagonally arranged carbons, right? And these sheets are layered on top of each other, kind of like very flaky chocolate we were talking about in class, or something. Imagine some very flaky food, right? And between these sheets of carbon, and that's what graphite looks like. If you pick it up and if you try to crush it, it'll come off in flakes. Between these sheets of graphite, because of the electrons, there's some weak forces of attraction between them. So it keeps graphite together. It holds it in place, right? But these graphite sheets can slide on top of each other. So if some force acts upon the sheet on the top, it can literally move on top of it without breaking the attraction. Once it moves forward, the newer carbon atoms will start attracting the carbons which they're later aligned with, and the sheet stays in position, so it doesn't really break. So the sliding function gives graphite another very cool property. It can act as a lubricant. So graphite, just because of this property of carbon not bonding to, not having an extra bond, well, extra is the wrong word, reducing one bond from 4 to 3, those electrons are free to move, so they end up drastically changing properties. Even if you've seen graphite, it looks very different from what diamond is. Even though if you take diamond, let's say if you take 10 grams of diamond and 10 grams of graphite, and if you burn it, they'll give off the same amount of smoke, right? Because they're just carbon, it's just carbon. Unlike diamond, graphite is soft and slippery. That is because the sheets can slide on top of each other. And unlike diamond, it is a good conductor of electricity because those electrons are free to move in the fourth bond, from the fourth bond that never gets bonded in graphite. So it's free to move and it can carry a current if it wants to. Here's a summary for macromolecules. We talked about 3 different kinds: diamond, graphite, silica. Diamond is the hardest known substance and does not conduct. Sparkles when cut. Okay. I guess it's so hot when you cut it, it just sparks. It's very pretty, so you use it in jewelry, but it's also used for drilling and cutting. So the edge of drill bits that are designed to cut hard metals or very strong metals is made of diamond, just the tip, right? Because diamond otherwise is very expensive. So you call these drill bits diamond tipped drills. So you might have seen 1 or 2 of them. Graphite is soft and slippery just because it can slide on top of each other. It still has a really high melting point though, not as high as diamond. I think it's around 2700, where diamond is, we saw 3550. It's soft and a dark color solid and conducts electricity, and we know why. Uses for graphite are lubrication for engines and locks. Why do you use graphite rather than oil is when the other oils can easily evaporate away, especially in an engine or machinery that operates at high temperatures. Oils over time will evaporate away. Where graphite, even though it's a lubricant, like acts as a lubricant, has a really high melting point because again, it has strong carbons are held together by strong covalent compounds, which are really, you'd need an insane amount of energy to break them. But it acts as a lubricant at the same time because those carbons are in sheets which are practically unmeltable, or like really high temperatures required to melt them, but those sheets can easily slide on top of each other, and that's what makes it a good lubricant. And it can conduct electricity, so you make electrodes out of it. Or carbon brushes are a thing which you'll study in physics, where the tips of some brushes in motors are made of carbon because it's just a suitable material to use there. Silica is also hard, and silica is sand, by the way. Silicon dioxide, silica, it's just sand. And it has a really high melting point. You use it in sandpaper. So sandpaper is just paper. If you've ever seen it up close, sandpaper, what they do is they take a sheet of cardboard, put glue on top of it, and sprinkle silica on it or sand on it. Once it's cured and it's dry, you literally pick that sheet up and it's ready for use. You rub it against something and it's gonna sand anything off because the particles are really hard. Silica is also the same thing as glass. So if you superheat sand, it turns to glass. It's just how structures are slightly different, and it can rearrange itself when you heat it really high and become translucent. And it's also used in bricks for lining furnaces. Hey, it's sand. Bricks is made of sand, right? Now, here's another summary for comparing between simple molecular substances and giant covalent structures. Molecular substances have low melting points. This is because the forces between molecules in a lattice are weak. So if you see something with low melting or boiling points, for sure, you should be confident it's a simple molecular structure. Again, examples would be carbon dioxide, you have water, you have just oxygen gas as well, you have nitrogen gas, right? All of these are simple covalent compounds. How do I know this? They're all gases or liquids at room temperature. Giant structures, on the other hand, like sodium chloride, notice how it's saying giant structures and not giant molecular structures. Sodium chloride is a giant structure as well because it's a large lattice of never-ending ions, right? I keep emphasizing that. Diamonds, silica, they're all giant structures, where this is giant ionic and this would be giant covalent. That's the difference. We'll have really high melting points. And they have really high melting and boiling points because the bonds between the ions or the atoms within giant structures is very strong. Or, like they don't have weak forces. They're held together by really strong covalent bonds, whereas in simple covalent molecules, they're not held together. Only the atoms in a molecule are held together by some covalent bonds, which are very strong. But those, again, aren't holding the molecules together. Aapas mein. So it takes a lot of energy or very little energy to change their state into a gas. If not, they're already a gas in the first place.